be starting with this URL. Let me switch over to my screen here. And we have the URL for today's notebook. So everybody's typed it in. It should take you to something that looks like this. Is that right? Excellent. Now here there is this little button that says Open in Colab. And if you click on that, it should open up a thing that looks like this. And when you click on Connect, it will probably say this, oh, you must be logged in with the Google account. That's fine. This will take me a second. And hopefully you are all already signed in and not using a computer that hasn't been used in 2 weeks. So you will be set up. OK. And so here we have our notebook. Has everyone used Google Colab here before? Yes? OK, excellent. Come on in. All right, so while you're getting ready, have you used Google Colab before?
Yes, I have.
OK, excellent. All right. So I'll just go back here. This is the URL that we'll be using. And I can start sort of talking about what we're going to be doing today by looking at the notebook. So the title of this workshop or meeting is SQL and NoSQL databases in Python with Pandas. There's actually very little Pandas and not a lot of database, but a lot of me sort of talking, unfortunately. We had a similar meeting almost exactly 2 years ago in March of 2023 that has its own notebook that's on our GitHub that has a lot of, as you can see, like a lot of code for making a fake data set and then turning it into a database, et cetera, et cetera. But I skip a lot of that to do other things instead. So here, let me bring the URL back up. So this is the URL to the notebook. And who here has used databases in a intentional way, as in you've written a query to use a database before?
Long time ago.
So all of you? Was it a SQL database or NoSQL or both? Or you don't know?
I used SQL long time ago, but
So
I
SQL.
don't have very clear memory about it. Yeah.
Has anyone used a NoSQL database? OK, excellent. That's perfectly fine. You probably have used NoSQL databases a lot and just don't know it. Because they are the backbone of a lot of stuff. So do you have this link opened already? OK, excellent. So it takes you to a notebook, and then you just click on the Open in Colab button, and then it'll open it in Colab. So SQL is, you're all familiar with it, more or less. So it's a language of doing queries, but is also used sort of synecdochically for a paradigm of creating databases, usually what we call relational databases, where you have a bunch of tables that are related to each other in some way. So and each item of data that you have, each datum, is stored as a row in one of those tables. So I have an example here where you can have, say you run a store and you have an orders table and a customers table and a products table. So when a customer, so one table is a list of your customers, one table is the list of the orders that the customers make, and the last table is the list of the products. This is very simplified, but the basic idea is that you have each order belongs to a specific customer who's the person that made that who made that order. And you can then start doing more involved queries. Jeremiah, can you set this parse up with the URL too? Thanks. You can then do sophisticated queries like show me the zip code of every customer who ordered a TK421 widget in the past 3 weeks. So that involves hitting all three of the tables that we mentioned. You use the products table to find what the ID is for the TK421 widget. It might be TK421 or something else. You use the orders table to find every order that has a link to the TK421 widget in it. And then the customers table, which presumably has their shipping address as one of the columns in their row, that then has their zip code. So you use all three, you hit all three of those tables to make a report like that. Show me the zip code of every customer who ordered a TK421 widget in the past 3 weeks. Oh, the orders also have a date when they were placed, so that's how you can get the in the last 3 weeks. And this is actually pretty easy to do in SQL. I'm not going to be going into great detail on the queries. We have a couple SQL queries at the end of the notebook, and I'll talk about them there. And one of the great things about SQL or relational databases is that they have a very rigid structure and transaction model. And what that means is that if a table has a certain number of columns, that's it. It has that certain number of columns. You can add and remove columns, but it's not really designed to do that. You're not supposed to mess with the schema all that much. And that kind of rigidity also allows the ACID principle to be maintained, which is atomicity, consistency, isolation, and durability. And basically what that means is that you can rely on these relational databases to run an online bank or run a bank, period. Because what happens if you are trying to, like, all the bank accounts get a small amount of money of interest at the end of the month. Say your servers go down while you're adding the interest to every single account. What do you do? So relational databases in SQL, they have a good transaction system that will make it possible for you to roll everything back and make sure that you always know that no one's getting paid twice, no one's getting, that the numbers all work out. So it's very rigid. NoSQL or not only SQL. Nowadays, NoSQL stands for not only SQL. I think when it started, it meant just like not SQL because it was something different. NoSQL is how we kind of think of the rest of database paradigms that you use. There are basically 3 that I'm familiar with. Key value stores, which is exactly what it sounds. It's just a key and a value, so there's no table, no nothing. Then there are graph databases that you have the relationships can have data associated with them, and document stores. We'll be looking at extremely briefly a document store today. They are not as reliable. They're not flaky, but they're not as reliable. And the cost of that, or the benefit of a slightly less reliable system, is that you gain a lot of flexibility. So these NoSQL databases aren't rigid with the format. You can sort of, every time you add a new chunk of data, it can look like whatever you want it to look like. So, the document store is a great metaphor, and I sort of describe it here. You can think of a document store as kind of like a box that has documents in it. So think of the box you have in your closet with a bunch of documents. Each of those documents is somehow different. One could be a letter, one could just be a photograph, one could be have a receipt stapled to it. Like, it's all different kinds of data that doesn't have a predictable format. The only thing that's predictable about it is that it's a document. So that's how NoSQL databases work. They make no prior assumptions on the structure of the data. So we can think of the customers data, the customers table earlier. There would be like a customer name, customer street address, customer zip code, customer email, customer phone number, all that sort of stuff. And the relational database might make it so that you have to have all those things have to be filled in. They can't be null. They always exist, etc. The document store just doesn't care. Sometimes there's a name, sometimes there isn't. Sometimes there's an email, sometimes there isn't. So this is a really different way of thinking about data being stored. And the document usually ends up, who knows how it actually looks for real on the database side. But when it comes to us, we usually see it as something that looks like either a Python dictionary. Did I write dictionary or document? A dictionary in Python, or an object in JavaScript, or like an XML document. So so we'll see in a second what it looks like, and it'll be very familiar. So I write here that the loosened ACID requirements on NoSQL make a lot of the internet possible. And that's because a lot of social media type stuff, etc., I was asking DeepSeek last night, I think, whether it's true to say that social media would not exist without NoSQL databases, and DeepSeek was like, well, that's mostly true, but you're saying you're overloading it a little bit, and that's fair. It's not completely true, but it's basically true, because what happens is the reason you can sit there and click stars in Netflix on movies and just go click, 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 and it doesn't take any time, and Netflix starts reloading new movies for you to rate, or on Facebook, you type in a Facebook post and click submit and you immediately see it. The reason it's able to do that is because it doesn't have to make the entire database for the entire world consistent. It just has to eventually be consistent. Whereas with a relational database or in a strong ACID environment, you have, like, the database has to be updated and has to be in a new state that has your new rating in place before it can go on. So a lot of you are maybe too young to remember this, but it used to be the case that, like, whenever you did something on a website 25 years ago, like you clicked a button, you had to wait because it was making a change on the database that was the database that everyone used. Whereas now it makes a change just that you see, and eventually that change propagates to the database. So that's something that NoSQL can make happen. And like I write here, this is oversimplifications, but it's basically right. The flip side is online banking couldn't exist without SQL databases, without and without ACID, because you need that reliability and that kind of you need to be able to trust everything. Yeah.
But does that mean the NoSQL is lack of the admin function? Because I know SQL is very strict with the admin thing, right? Even though you can regard it as dynamic database, but admin will decide how, when to update the thing. And as you described for the NoSQL thing, it's like more flexible. So everyone could be the admin. You decide what to add on.
Yeah, well, both databases, you can grant different kinds of privileges on different kinds of aspects of the database. But the overall idea is correct, that the admin sets the framework of the relational database, and you can't necessarily just like automatically decide, oh, you know what, we want to also have our customers' Twitter names. Whereas in a NoSQL environment, you can just add a new key that's Twitter name or whatever. And sometimes that works and sometimes it doesn't. So, I like giving these examples because if you go on the internet, there's a lot of pages that are like, well, which one should I use? And the answer, or like, which is better? And there isn't really an answer because these are very different use cases. When I was asking DeepSeek about and I typically don't ask AI, I just wanted to see about this thing. But when I was asking DeepSeek about the thing about social media, it used a phrase that I hadn't thought of, which was user expectations. that user expectations are made are met better with a NoSQL thing. And how I understand that to mean is that you click on something and that's all you have to do. You don't have to click and wait for it to call up the database, save the things. Like in this kind of environment, you can cache all the changes here and then eventually push it to the database, and then eventually the database gets in sync with all of its mirrors and whatever around the world, so everyone can see how you rated a movie. But what you care is that it immediately happens for you. Maybe rating the movies isn't the best example, but like posting to Facebook. Like you want to see your post immediately and not have to have it go all the way to the data center and back, etc. So MongoDB is one of the better known document store databases. And this is, all these database servers have clients in JavaScript, Python, whatever programming library you want to use to do stuff with them. And this is using the node, so the JavaScript client is just a bunch of stuff. And to me, this is eminently legible what's going on here. So database fave foods. Fave foods is a collection. So a document store, you can have something that looks a little bit like a table in it. You can have a thing called a collection, and insert many. So each of these lines here is its own document. So, and we can see, like, they all have a name, they all have a cuisine, not all of them have toppings, and that's fine. Like, it doesn't matter. So all four of these things are, again, documents, and they get saved. And then I can just do a search like this, like find where cuisine is Mexican. And then we can see this in action. Let me go over here. So if you click here on this in one compiler, it'll take you to something that looks like this, and you can see it in action. So this is just some JavaScript. And we can see the output of the insert many. It acknowledges that it happened, and it gives us these IDs that are, they're unique. I always get this wrong. They're at least unique to the server. So these are the IDs. And then if I do this search, find cuisine Mexican, it gives me these IDs that aren't super useful for me. And then it gives the name and the cuisine and then the toppings, if toppings is part of the thing. So this is just a very basic example, but just to show just how just very flexible it is. And I mean, I can create a new, I shouldn't be live coding this, but I'm pretty sure I can just do customers, insert many, just myself, and then run. And it just lets me create just a new collection called customers. Like, this is all just set up out of the blue in whatever VM this is, who knows. So very, very flexible. SQL and relational databases are not this flexible. No way, no way. And so if you're familiar with Python and JavaScript, this should be pretty legible. So we're about to jump into the SQL, but I wanted to, Data Club has a no free ads policy, but I did want to do a little ad for Baserow. Have any of you used Airtable before? No? Do any of you know what Airtable is? Okay, that's fine. I haven't used it much either, but I'm not positive that Airtable was the first to do this, but it was the first time I saw it, and I was like, holy smokes, that's smart. I wish that this existed in an open source version, and the open source version is called Baserow. So what Baserow advertises itself as is a no-code open source database. So they say goodbye to spreadsheets. And you can see what you get instead. Instead of spreadsheets, you get spreadsheet-looking database tables, SQL database tables. You can run Baserow on your own computer for your own private stuff, and in the background, what it does is it spins up a Postgres database server and sets up a relational Postgres database with a bunch of tables that do things that let you use them in a SQL fashion. And then it does some other stuff too. And the reason I wanted to show this is because I created, like, on my you can also host your things on Baserow itself. They let you have up to 3,000 rows, which is actually not that many. Like, that can get filled up really quickly, but that's also enough to see what things are like. And so I created a Data Club workspace, and then I have a Data Club DB here, a Data Club database, and then I have two tables, songs and DJs. So this is the first opportunity for you all to do something and not listen to me talk, which is you run this first line of code here. Here's where it says this is not done by Google. Run anyway. And it installs an API, or the Baserow API. The other really neat thing about Baserow, and Airtable does this too, is if I right-click on the database, oops, I have to right-click somewhere else. Oh, I click here. And I do View API Docs, it shows me examples of how to do API calls to this database in, like, JavaScript or Python. This is such, like, I'm literally having tingles because this is such a great feature for users. So if I go to, like, the DJs table, it tells me, oh, here are the fields, here are filters that I can do, equal, not equal, contains, et cetera, and I can look at different, so it tells me all the properties and gives me examples of how to do requests and what the responses look like. Like, this is amazing. It has built-in API documentation for your Baserow, and you can, like, control who has access to this sort of stuff, et cetera, but I'm just blown away by this. Airtable does it too, but yeah. Okay. So step one is install the Baserow API, which lets us talk to Baserow via Python. The next one is some constants. This first thing, the token, is a secret. It's okay that it's going to be on YouTube, whatever, because I'm going to delete it after we're done here. But this is a secret with which you now have full access to the database. The DJs table has an ID of this, and the songs table has an ID of this. So if we run this, and then if we do this, we get a table, right? So Baserow equals Baserow, and then the URL is just the regular baserow.io. I'm just using the free version there that's hosted on Baserow, whatever. You can put in if you're running it on your machine, you can do localhost, whatever. Token is the Baserow token. And then I get the table DJ's ID, so this table here. And then, like, this isn't very helpful. It's an object that we don't know anything about. But I can do this, and I get a table of, a list of Python dictionaries that are the people in the DJs table. So I'm one of the DJs, and then the other one is DJ Kinch, which is a fake name I made up literally 30 years ago. And next, this is where it gets interactive, is you can type in your name here in DJ name, and if you uncomment added row and press play, I should start seeing this populate. Don't be shy. There you go. All right, excellent. So yeah, so it's filling up with your names. Thank you for participating in this. And with your DJ names. And that's that. So we connected via the API, and what you were doing was a SQL insert statement, inserting a new row. And so now we have, if I do this again, we now get all of you who added your names here too. This isn't that impressive. What's in the big picture, like we expect the internet to work this way, what's impressive to me is that this is being done specifically through SQL calls without having to write a single line of SQL code or a SQL query. Next, we can do the songs. So I put in 2 songs. I was trying to think of what kinds of songs would be appropriate for Data Club. So Computer Love is obvious. The song Apple might not be as obvious, except it was, I don't remember which version of the Mac operating system it was, but it was the song that was played in the welcome when you got a new Mac, whatever. So I thought of a third song, and you can fill these in however you want for yourself, and do this. Don't uncomment this though. We'll be doing this later. So you can fill this in as you like, and you create a variable called new song. But if you go to Baserow, you can see that I'm set up with songs here. This links between the DJs table and the songs table. And under the songs table, let me try to minimize some of this stuff. Under the songs table, you can see that my name is here, because this is the relationality of the database table. So it's the songs table and the DJs table are linked. Every DJ has multiple songs, and every song can have multiple DJs. It should only go in one direction, but by default, they let it go in both directions. So how do you link up yourself? Is you can go to DJs get rows and filter based on your name. You know, whatever you typed in for your DJ name. And then I just have this all with my name, but you end up with an ID. That's a number. So for me, it's 1 because I was the first person to add myself to this. If I go here and go to DJs, I can see like, Wei, I'm guessing this is you. Mm-hmm. Your ID should be 6. Okay. If you type in WY in that line of code here, if you type in WY, then this should be 6. There you go. That works correctly. And
but
so
I still use Mozilla ID.
Yeah, that doesn't matter. It's just the variable name. I probably should have given it a more general name, but oops.
No, I mean, I just wonder if that's the case.
Yeah. So, so you get your ID, and then you add a field to new song DJ equals Moisir ID. So I have to change it back to me because I want credit for the Janelle Monáe song, not you, Wei. Mm-hmm. And now if I do, oops. So I do this, and now let me just rerun this again with new song. New song is just a regular, boring, old Python dictionary with DJ set to 1, Moisir ID. If DJ were set to 6, then Wei, you would get credit for this song. Mm-hmm. If you were to type in your own stuff here, then you'll get credit for it. And then I do, I can just delete this and then do added song again, or added song. Then when I do this line of code, it shows, the new song shows up. And it shows up here in the grid for songs.
But you don't have ID. Why you don't have the 1, 2, 3, 4?
Here, you mean? Mm-hmm. This is because I made a mistake when I was setting everything up, and it accidentally. So So Baserow had, these are the real IDs, 35, 36. This is just a column that it's using as the primary key, which it's a mistake I made. So it's okay that it's empty. I would, yeah, that's why.
But why after 1, 2, the ID number, then it's 35 and 36?
Because that's a very good question. It would make it seem like I tried this 30 times in between.
And you removed it.
And then just removed them, yeah. So if you look at the DJs, for example, you see it goes 1, 4, 6, 7, da, 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 da. And Henry signed up 4 times.
I see.
So then, like, this curiously has unnamed row 30. Oh,
Yeah.
okay.
So that's the thing.
Yeah, so that's because this is actually trying to read the contents of, here, let me do this. Edit field, link to table, select a table to link to, that's correct. Okay, I can't. I would be able to have the song name here, but I'm not going to figure out how to do that now. This is just a convenience sort of thing here. But if I were to fill this in with the name, actually, let's give that a try. Why not? Let's have some fun. Let's change the primary field to song name, change, and then delete this field. And now let's see what happens here. So now it brings in the name of the song. The problem is that I have Electric Lady associated with me, as does Eliza, DJ Eliza, but they are different instances of the same song. See, here it's me, here it's Eliza. So this isn't a unique identifier. This is the unique identifier, these numbers here. So if you do the ID, you'll get 35 and 30. So if I if I go back to here, and then I do this again, you see it says DJ Eliza, DJ Moser, and if I go here and show all the DJs again, it has the names of the, it had the numbers earlier, but now it replaced them with the song names. I mean, these are implementation wrinkles that Baserow does, but again, it's pretty neat because it does link the things together. So I guess my ploy to get you to add real songs to the Data Club playlist didn't work. You're all shy. That's fine. Okay.
There's not enough time to find the YouTube link.
That could be. Well, I won't nuke the API key for another hour or so. So if you find a song or think of one, then go ahead and add it. Okay, so now let's talk about SQL. What I did here is this is all from that meeting from 2 years ago. Basically, a couple of students put together a SQL database of Pokemon. It's something that's like 750 Pokemon or something. And they shared it on GitHub. I forked it. And then I made a couple teeny tiny changes to make it more straightforward. So this isn't code. This shows what I wish we could do, but it doesn't let you do this in the Colab environment. So I had to pull the database, the .sql file. Then I had to turn it into a MySQL database on a MySQL server on my computer, and then had to convert the MySQL database to an SQLite database. This is something that hopefully you would never have to do, because the key thing here is setting up the database is not typically something that you should be doing. That's a database administrator is doing that, and what you're doing is you're trying to connect to the database in some way. So that could be with something like the API key in Baserow, this API key. That could be with a username and password to a MySQL or a Postgres database, and then using Python libraries to connect to them through Colab. I think in the secrets, you can add secrets to also be able to use passwords and stuff inside of Colab without putting them in the world. Anyway, what the short version is what ends up happening is I created a SQLite, which is SQLite lets you create a SQL database that is saved as a single binary file on your disk that you can then upload to GitHub or download from GitHub, et cetera, et cetera. So if you scoot all the way down here to where it says import pandas as PD, this lets you do that stuff. So I have this URL that I made ahead of time that downloads this SQLite Pokemon database. It gets it from the internet, and it writes it to Colab. And you know it worked because if you open this folder, it'll say Pokemon.SQLite here. So I'll give you all a second to run that bit of code and to have a sip of water. So far, so good. Any questions? Excellent. OK. Now, things get a little bit magical here. And by that, I mean we're using these percent sign things. Have you seen these little commands with percent signs in front of them in Jupyter Notebooks or Colab Notebooks before? They are like literally called magic commands. And you have seen some, because if you try to, oh no, that's with an exclamation point. Oftentimes if you do a pandas, if you do the import pandas, import matplotlib, let's see if the AI does it for me. Import pandas as PD. Nope, import numpy as MP. Stop telling me, I'm expecting it to go import matplotlib. Mat, let's go. Matplotlib, there we go. As PLT, fine. And then, there it is. I didn't even have to Google it. Matplotlib inline. So you've likely seen this before. If you've ever done matplotlib plots in a Jupyter Notebook or in Colab, this is a magic command. I think that's what it's magic something, magic command, magic whatever.
Even in Jupyter, you should.
Yeah, in Jupyter Notebooks, you use them too. So this is something config SQL magic.style. So this is just a little thing that we have to run so that it works. Didn't have to do it in 2023, but now you do. And then we do these things. So the important thing here is this SQL magic command, percent SQL. So you load it with load x SQL, then SQL, SQLite, Pokemon, SQLite. So what this means is it loads in the SQLite file that we downloaded from GitHub, that binary file that is now here. It loads that database into memory. And we access it, we query it by doing something with the SQL magic command. So like it says here, run SQL statement against the database. And there are, like in the example they give here, SQL PostgreSQL : // like you can connect directly to a external server using this. So we'll run some queries, but first I have to describe this database. So this is what the database looks like. It's so complicated, I have to zoom out to show it. Have any of you seen pictures like this before? This is an ERD, I think it's called. Do you know what these lines mean? Yeah, go ahead.
I think that's, if I'm not mistaken, that'd be the connection from the primary keys to foreign keys between tables.
Right, exactly. Yeah, so it shows relationships, and then the relationships are sort of color coded here a little bit. But you're exactly right. The little arrows, or it's not really an arrow. This shows a one-to-many relationship. One-to-many. It's sort of many because this forks out, I guess, is how I remember it. And when you have a many-to-many relationship, like one Pokemon can have many abilities, and one ability can be associated with many Pokemon, that's a many-to-many relationship, which there is no way of natively doing that in SQL because it's complicated. So what you end up doing is you have an intermediate table that is typically called both of the table names with an underscore in between, so it's called Pokemon abilities, that has the Pokemon ID, so that's the foreign key. So here it's the primary key, Poke ID, that's what the little light bulb means. I think this is a light bulb. Poke ID is the primary key, the unique identifier for Pokemon. It's a foreign key here on Pokemon abilities. Then you have Abil ID, which is also a foreign key, but the primary key on abilities. So this table, all it is it links a certain Pokemon to a certain ability. And that works to let a single Pokemon have many abilities and a single ability to have many Pokemon. So far, so good? It's not going to get more complicated than that. But this repeats itself throughout. So we see Pokemon types, for example. A Pokemon, I don't really know all that much about Pokemon. Jeremiah is the Pokemon expert. But apparently, a Pokemon can have multiple types.
Yes.
Okay, but like that's implicit here because this is a one-to-many relationship, and a type can have many Pokemon. That part makes perfect sense to me. A Pokemon can have many moves, and a single move can be done by many Pokemon. So what follows can be repeated for all of these things. I'm just going to focus on two things: the base statistics and the abilities. So one of the ways we can sort of get our grounding in is running the pragma SQL command that can give us the table information about a certain table. So this thing is effectively, or should be, more or less identical to what's here. So we have a poke ID, yep, int 11 integer, excellent. Poke name is a varchar 79, perfect. Poke height, poke weight, poke base experience is all set to this. What is the base experience? Do you know,
No.
Jeremiah? No? Okay. I didn't include it in.
Because they have levels.
Right, but what does the base mean? Like did they start with a certain amount of?
They don't start in 0. They start at something.
Okay, so maybe we have a new Pokemon expert. Yeah. So all right. So they start with a certain amount of experience already, and I start with this query, and there's a ton going on in this query. But this is what SQL looks like, in case you've never written it before. Wei, you said it's been a while for you, so
It's SQL, I know.
yeah.
But I don't know, will you link this to non-SQL? This is the SQL database, the Pokemon.
So the Pokemon database is a SQL database. So we're gonna do two queries more or less. What this query does is it selects the Pokemon ID from the Pokemon.pokeid is the Pokemon table.pokeid, which we saw exists up here. The Pokemon.pokename, basestats.battack, and then a bunch of other ones, which we know are from here. Or I could do pragma table info base stats to see them. But these are a bunch of, so attack, defense, hit points, I'm guessing, speed, special attack, and special defense. So from Pokemon, so from the table Pokemon, inner join base stats. Inner join, I should have looked this up. Inner join, I think, means that the result will only be when you have hits on both tables, when they match. That's what you get in an inner join. So it will only give us results when a Pokemon ID is on both rows. I think that's what an inner join is. So that's what this is. On Pokemon.PokeID equals base stats.PokeID. So Pokemon.PokeID is the primary key. Base stats.PokeID is the foreign key. So this is a basic one-to-one relationship. There's no. I wonder if it has the drawing that way too. No, this is one-to-many. I don't know that it should be. It should be one-to-one, but it's weird that it's its own table anyway. Like, why is height and weight in Pokemon, but base stats isn't? I don't know.
Do you think it might be related to the base level? Because the stats move with the Pokemon level, but the weight and height are like given. Your Pokemon won't get like fatter or like taller.
Right.
Or it will get like stronger and faster.
That's a great possibility. The only problem is there's no way to tell that from here, in the sense that the only way that we can link the base stats to the Pokemon is on the Poke ID. And the Poke ID is unique to a species or something like that. So it doesn't also, if it also had something like a level delimiter, then something like that would make sense. So
you will have to have something else there.
Right, yeah. So, but yeah, the way this is set up, it's not completely clear to me why it's its own table, even though those stats are variable. There has to be something somewhere is missing to account for that. Thanks. So we run this query, and how this works is you do the SQL little command, and then you create a variable name. In this case, it's strong Pokemon, and then you do less than, and then you type in, let me finish the query, where B attack is greater than 100, and B defense is greater than 100, and B hit points is greater than 100. Because my idea was that these are what strong Pokemon look like. And it exercises the query, and then I can see it. And at first I was like, why is it only giving me the first 5 results? The answer is there are only 5. There are only 5 Pokemon that have attack greater than 100, defense greater than 100, and hit points greater than 100. So I don't know any of these, but you tell me if they are powerful tanks. Now, this variable strong Pokemon that we created up here, we can also turn into a data frame with the data frame method. And now it's just a regular data frame that we can read in Pandas, which means we can do something like sort values by B attack. I think this will work. Yes, they're ascending, but there we go. So that's just regular basic Pandas. If you are not familiar with Pandas, I have a workshop that's online, or online in general. But we're not doing anything complex here. The complex stuff is at our next meeting. Next query. This query is so complicated, I have to zoom out. So this does all the same stuff with the stats, except it renames them to slightly more legible things. it also grabs the height and weight of the Pokemon. And then it takes its abilities and concatenates them into a comma-separated list. So you can see that it's the main table it's thinking and looking at is the Pokemon table. But then it also looks at the base stats table, so the same way as earlier, except this is a slightly more terse syntax. And then it does another join on the Pokemon abilities table, which remember is the many-to-many table that just links an ability ID with a Pokemon ID. And it does another join on the abilities table to get the abilities name, because Pokemon_abilities is just 2 IDs. It's useless, just 2 numbers. So the last one is it takes the PA, Pokemon abilities, abil ID, and matches it to A, abilities, dot abil ID, and gets the name that way. And then it groups by Pokemon. And then if we run this, and then I do Pokemon, we get all 721 Pokemon. And we get, I'm just scroll up to the top here. Scroll, 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 scroll. Okay. And we can see that they have the ID, they have the name, height, weight, et cetera, and you can see that the abilities are here in a comma-separated list. Yes?
Could you go over what group concat does again?
Sure. So group concat is how we end up with this here, but I'll describe it in more detail in a second. So group concat takes all of these abil names and concatenates them with this separator of a comma and then a space, and treats it as the column abilities. So because we have this group by at the bottom, so we would end up with a bunch of rows where we have one row that's Bulbasaur with all these stats and then overgrow. And then another row that's Bulbasaur, all these stats, and then chlorophyll. So these would be separate if we did a normal search, because it just gives us where there's matches. So because we do the group by here, then we end up with a group on the abilities as well, so it just smushes them into a readable comma-separated list, just like this.
Could you show the original format of the abilities table?
Sure. The abilities table is just an ID and a name.
And when you do that concatenate, they only pick the name, right? So
Right.
you indicate, and that's a string? Oh no,
Yeah.
that's a list or whatever. That's my question.
It's a good question, because this is tricky. So you have to remember that this is a many-to-many relationship. So Bulbasaur has Overgrow and Chlorophyll as the 2 abilities. Mm-hmm. So under a normal merge, you would have Bulbasaur twice, right. Once with Overgrow, once with Chlorophyll. Mm-hmm. So that's what's happening here, is that there's a row that has Bulbasaur's ID and the Overgrow ID, and then Bulbasaur's ID and the Chlorophyll ID, like in this table. But through the grouping, it smushes all of the abilities into just the one Pokemon, and just makes a string out of them, just smushes them together by doing a group by. So it's.
But you didn't do the between. You used the abilities, right? When you do the inner join, you inner join the Pokemon and the abilities rather than the middle table or
yes,
database.
No, that's exactly correct, because so here, so abil name, this is an alias for abilities. Right. So it's saying take abil name that exists on the abilities table. Mm-hmm, mm-hmm. So it's just keeps adding columns as it keeps doing joins. So it does this join on, so this is the middle table. Join them based on, yes. Oh, yeah. No, you need the middle table, because that's how it links everything up. So this join is linking a specific Pokemon ID from the Pokemon table with the Pokemon abilities ID. Mm-hmm. it makes the link there. And then there's another join on the abilities table that also links to the Pokemon abilities table. Yeah, I mean, this is hard, and it's very easy to make a mistake. I made many mistakes while getting this together today, but once it works, it works. And this is a reason why very often people just say, I'm not writing SQL queries anymore. I'm going to use something like Pony ORM, which is an object relational mapper, which turns, which would turn Pokemon into a class, ability into a class, and base stats into a class, and then you could find these links automatically. And it does all the SQL stuff in the background. You don't have to think about it. But it's also kind of important, I think, to see what the SQL looks like, because the SQL is what's always the same. This syntax is the only wrinkle in the syntax that changes, as far as I know, between different kinds of SQLs is the group concat. This command, the arguments this command takes depends on what kind of server you're using. This is what it looks like for SQLite. Okay. So those are all the Pokemon. And then, like I said, we have this list, but instead I want to one-hot encode the abilities. Does anybody know what one-hot encoding is? Yeah.
I think it's updating the labels to be numerical.
Yes.
Right.
Yeah. So we can think of the abilities as a categorical data type. The problem is that each Pokemon has at least one ability, if not more. So we can't really treat it as a drop-down menu, right? If we're trying to think of how to filter this or something like that, because currently it's just a string with commas in between. But we want to be able to say something like how can we find everybody that has inner focus as an ability, but not without having to do a weird kind of like is inner focus their first ability or second ability or third ability, because these aren't sorted in any direction. Like, let's say there was a Pokemon that had chlorophyll, inner focus. Then you would have to know what, like you would have to do these kinds of searches on strings, which is not the most efficient way to do this kind of stuff. What one-hot encoding does is it makes categorical variables numeric by sort of doing a bit of a pivot. So instead of having a list of 3 abilities for a single Pokemon, we're going to end up with n columns, where each column is one ability. And then if the Pokemon has that ability, they get a 1 there. If they don't, they get a 0. I think that's why it's called one-hot. I'm not sure what the hot means, but that's what one-hot encoding is. So it's a way of, if you had categorical, like colors or something like that, where red, green, blue, then instead you sort of pivot and you end up with a column for red, a column for green, and a column for blue, and then it's 1 or 0 or 1, 0 or 0. So this is basically when you're training a model in machine learning, you do this because you want to, you typically do it and then drop the first column. These are very correlated columns. But so sometimes you may even have to drop them anyway, but it's a helpful way to numericize categorical data. And especially if you have these kinds of many-to-many situations. So that's what happens here. This is a little bit silly because I split the abilities column based on comma space. Then I just join it back together, and then I use Pandas's built-in getDummies method, and then concatenate it back in with the original data frame. And now we have this thing where all of the abilities are encoded here. I don't know how many abilities there are. There's code later on to find out, but I don't know. And we can see that none of the first 5 Pokemon have Wonder Skin. But if we do a search for Pikachu, we get Pikachu, and we can then, how did I do this? Oh, we can see if Pikachu has lightning. Oh no, I have to do this way. Lightning, come on, what's it called? Lightning strike? Lightning by itself? Nope. All right, give me a sec here. This is where all the ability names are. So I can just, oh, they're not sorted. Oops. Let's see if I can get lucky. Lightning. No, I'm not going to get lucky. Okay. The problem with this is that there isn't an obvious way for me to see what abilities Pikachu.
Lightning bolt.
Lightning bolt?
Rod, R-O-D.
A lightning rod.
Light, N-I-N-G-R-O-D.
There we go. So Pikachu has a 1 for lightning rod. Thank you. And we can do a search for all the Pokemon that have lightning rod as a power. So there are 15 of them. I know Pichu, Raichu, and Pikachu. That's it. So they all have lightning bolt or lightning rod as a power. And you do that by doing the equals equals 1. So that's one of the, like we could do a string search also, but this kind of one-hot encoding, again, if you end up doing something like machine learning, you will want to do something like this. And that's about it, except that I then, oh wow, this took up almost all the time. I wrote here, oh, this is ETL, right. So one of the things that I'm trying to focus on this semester is on ETL, which is extract, transform, load, which is a kind of workflow for dealing with data. You know, if you're talking about something like data engineering, then it's concerned with pipelines like this. And this is what extract looks like. The goal here, what we end up with, so if I do df to CSV and just press play there, is I end up with a file here called Pokemon CSV, and then if I download it, and then sure, save to the desktop, and then if I open this file, do I just do this? Let's see what happens. Okay, it'll take a second. What we're doing here is we were taking the database, and this is a very simple and contrived example, but it's taking the database that has information scattered in all these different places in these different tables and just smushing it all together into a single table, a CSV file, that we can then use for analysis. And this is the extract. One-hot encoding is a kind of transform. Smushing the tables together is a kind of transform, but we've extracted from databases that have tables, all these different tables. You can imagine multiple databases where we're linking based on FIPS code for census data that has that encodes the state, county, census, what's tracked, and then block, with other stuff that may be encoded that way and making linkages across different data sets that share IDs, all this kind of stuff. This is the extract. Then the transform is putting something together into a column-oriented data set, which is what we'll be talking about at the next data club. And then then loading that into an analysis environment. Like one of the ways of thinking about data engineering is getting data in a shape that the data scientists can do something with. Because data scientists like a table of data that they can do math on, not having to write a bunch of SQL queries. And that's it, and that's what we'll be looking at. So here are all the 700 Pokemon with all their stats, and then just all of these one-hot encoded abilities. And we would be able, I don't want to give myself ideas about training a model on Pokemon, but we could do something like that. And that's it. I'll stop the recording here.